Yeah, great. So thanks very much for coming today. Today we have two speakers, but just to explain the background. So CBCS is supporting research in several different ways. And one way is to offer a grant opportunity. And this is based on these presentations are based on the CSIRO UQ collaborating funding, which opened earlier this year. And we had 7 successful started their project earlier this year. And today we have 2 applicants, 2 successful applicants. And we later in November, we have there's 5 applicants giving a presentation on their projects. Because these projects have just started, so today these 2 people will essentially explain what kind of project they are trying to do based on this collaborative funding. But I hope you will enjoy these presentations. Okay, great. So first is the Emer Cunningham. Could you please introduce yourself a little bit, and then we'll go to the presentation.
Yeah, sure. Hi everyone, my name's Emer. I'm a PhD student in what was formerly the School of Biological Sciences. We're now all in the School of the Environment. I did my confirmation in May, so I've just kind of finished the first year of my PhD, and I'll be talking about a very much ongoing project about ecological novelty in coral reef ecosystems. Yeah, so thanks very much for having me, and I guess I'll get started. Okay, cool. So I'd like to acknowledge firstly that we're here on Turrbal and Yagara land, meeting in Bayesian. And for this project so far, I also was able to spend time on Heron Island. And so I'd like to begin by acknowledging the traditional owners of this land that we call Australia and its surrounding sea country. I pay my respects to elders past, present, and emerging, and I recognise that sovereignty was never ceded. Our world's ecological assemblages have always been changing, but increasingly and under human influences, we're seeing really rapid and unprecedented ecological change. So much so that we've given the products of this change a new name. We're looking here at community states which have each been described as novel. Now, this concept of ecological novelty is relatively novel itself. Over the past decade, scientists from different fields have used different definitions and thus methods to try to characterize this very significant ecological change. The concept was popularized within conservation biology in response to specifically human-altered systems, looking at ecosystem change and often also degradation. And as a result of our haste to want to describe and to care for these massively altered systems, the concept sort of diversified without a general consensus. And this has attracted both criticism and also big collaborations to try to unify and direct our thoughts about novelty. And we've arrived now at sort of a general consensus definition. We're looking here at a pretty classic example of a novel shift, where on this Caribbean coral reef, its historical acropora-dominated state has transitioned quite rapidly towards a very different modern species composition. And this is a unifying theme amongst fields, is this idea that a novel community is characterized by having a significantly different community image. And having this general picture of novelty is critical if we want for the concept to be useful. Armed with a more quantitative definition, Pandolfi, Staples, and Kiesling have recently put forward a framework to help us to detect these novel states as they emerge through time, using the definition that a novel community forms through rapid change towards an historically unprecedented state. And it's this dual-factored definition. We're looking at both the speed and the extent of ecological change. which allows us to quantify those two components. We look at the dissimilarity between community states in a time series and look at them against our modelled expectations for ecological change through time. And this is quite place-based. This is using these grey bands that you see here. So that against a 95% probability threshold, it's the most significant instances of rapid or unprecedented change, which are then detected, and we can classify community states through time as novel or non-novel. But despite our quantitative advancements, the field is still largely descriptive. When we have been looking for more quantitative tools to help us find these novel states, they generally are found through time in historical settings rather than across the ecosystems that we know they are appearing in. And the bulk of our work, whether it's qualitative or quantitative, has been focused on land, despite the fact that we know our marine ecosystems are very valuable, but also very vulnerable. And the value and vulnerability of marine ecosystems, I think, can be typified by the corals along our coastlines. And it's these systems that I'll be focusing on for this project. And so for one of my PhD chapters, I aim to build the foundations for calculating and interpreting novel assemblages across ecosystems. To do this, I'll be altering that Pandolfi et al. Framework so that it can accept spatial data and make comparisons to look for novelty across ecosystems. I'll be explicitly manipulating different spatial and ecological features to see how that affects our resulting novel assemblages and how to interpret what a novel community looks like across space. And after developing and testing these methods, I'll be applying them across 3 different regions of East Australia and its coral communities. Taking us from Pondamuka or Moreton Bay, nice and close to home. In the southern Great Barrier Reef, we will visit Heron Island or have visited Heron Island. And in the very far north, we're going to Jiggaroo or Wollumbar, also known as Lizard Island. It's the corals of Jiggaroo that this funding is going to support a little trip to go visit. But that's in January or February of next year. So instead, I'm going to be talking about Heron Island for today. And we visited as a marine paleoecology lab the corals of Heron Island in September, October of last year. We went and surveyed quite a small section of Heron Reef, south of Heron Island there and bordering the Westari Channel, so we're along the reef slope, where all of these dots here clustered into 7 sites show us a point where we conducted a photogrammetry survey. And in these surveys, a snorkeler or a diver swims over a section of reef and captures thousands of images of the organisms below them, which we can then stitch into these photo mosaics. These are really high resolution, detailed maps of the benefit community composition that was captured. Our photo mosaics were sampled across our 7 sites at 3 different depths. So we're looking here at a single site, we're looking at Heron Bommy, where each of these dots represents a photogrammetry survey and their colours represent 3 different depths. So we looked at the reef crest, shallow reef slope and deep reef slope, which each represent different habitat types or geomorphic zones. And so having these 3 different habitat types at each of our sites allows us to have different environmental conditions, I guess, categorically, across which and within which we can develop and test our methodology. This is an example of one of our photo mosaics, which covers an area of 30 to 40 meters squared, which gives us a lot to work with. We'll be extracting quadrat samples from these really rich samples of Heron Reef. And so the first challenge, which is something that I am still embarking on, is actually developing this toolset using the Pandolfi et al. Framework and translating its ideas from temporal comparisons to spatial ones. So we first need to think about what to measure when we have our coral community data. And of course, I'll be measuring in both cases some sort of aspect of community composition. Looking at that through time, our difference will be across time blocks. So we might be measuring distance in years or months, but across space, that distance will be metric distance. We're looking at how our samples are separated across space. To compare these measurements, through time, we look for our two key signals of change. We're looking for rapid and unprecedented change. And that looks like comparing a coral community to its immediately preceding state versus all of the historical states that have been sampled at that particular site. Words like rapid and unprecedented, arguably even the word novel, are quite time specific. And so across space, we might be looking into ways to do sort of next door neighbor versus whole neighborhood comparisons, where we're looking at your closest sample versus everything in your surrounding ecosystem. Measuring these comparisons against expectations for change through time is something that we can model, but understanding our expectations for a novel community across space is something that will be a genuine challenge. If we think for a moment as to a big sample of herring reef, if we're imagining here these, these lagoonal samples here, we can see that they're generally dominated by this pink branching taxon, but we also have a sample where we see a community full of these green massive or boulder taxa. And within this lagoon, we expect for the depth to be consistent, similar tidal influences, temperature regimes. And so across that area, our expectations for a community being different would be quite low. We'd expect similar compositions within those similar environmental conditions. And so perhaps that green massive sample is going to be considered novel given our expectations for our spatial novel assemblages. But if we look at an example on Wustari Reef here, we have quite a steep drop-off when we get to the reef slope. And so when we see our different compositions within a close metric distance here, perhaps they will be considered non-novel compositions when we adjust our expectations so that it reflects the fact that this is a far more heterogeneous area of the reef. And so translating these ecological ideas into mathematical ones is something I might do this afternoon or in the next month or so. And one last thing I'd like to consider in our through time to across space transitions here is just the connotations that the word novel holds. When we're thinking through time, novelty generally tends to be a negative thing. I imagine things like disease or coral bleaching in these coral reef ecosystems. And especially under human exploitation and things like that in our modern age, novelty is not a good thing. But across space, while there's still potential to see things like species invasions or disease outbreaks, spatial novelty comparison may also show us areas that are biodiversity hotspots. We might note rare taxa across an ecosystem. And so being able to interpret what a novel spatial assemblage looks like is something that this project will uncover. To further our interpretation of spatially novel communities, I'll be working with different spatial and ecological features to see how they affect our results of the framework. Here I've highlighted an example of changing the size of our quadrats to show us whether or not the number and type of novel communities differs with that feature. using features like this and choosing the size of our quadrats, the size of our spatial extent, these are all decisions that ecologists and ecosystem managers need to be making, whether it's in their field work or in their desk work later. So I aim to make explicit the effects of these choices for anyone who may use this foundational method. And so there's a lot of work to be done in this project, but the aim is to deliver these first methods for quantitatively finding novel assemblages across space. I'll be specifically developing our interpretation of these spatially novel communities and hopefully applying them across those 3 different regions of East Australia to provide the first look into spatial novelty across different ecosystems, hopefully then giving us the potential to apply them to our other valuable and vulnerable ecosystems that we care about. Thanks very much for listening. Let's take some questions.
Does anyone have any questions?
Yeah.
So you mentioned that you are going to do technology. So I'm wondering what kind of data you're going to use. I'm asking because I think there are a lot of statistics and machine learning that can be used with the technology.
Yeah. Yeah, there's definitely tools not only in like statistics, but also economics. I have a co-supervisor who's really interested in the different sorts of equations we might be able to use. And I think that they'll fit in most relevantly when we are looking for expectations of ecological change through space. Because through time, we just create like spline-based models. So we're using GAMs for that based off of the historical samples that they've got. And so, yeah, that's an area that I'm still delving into. Yeah. But yes. Yeah.
To move on to the next one, just so we don't have time.
Yeah, sure. Happy to chat with anyone else.
Okay, so the next speaker is Nan Ye. Yes, please. Yeah, so I'm from School of Mathematics and Physics. I'm a lecturer of statistical data science. So people at the back, can you hear me clearly? Do I need to speak louder? A bit louder. Okay. Yes, so I'm in the School of Mathematics and Physics. I'm working on statistics, data science, and machine learning. Yeah, so thanks Katrina and Kate for organizing this, and also especially thanks to CSIRO and CBCS for funding this project. So what I'm going to talk about here, I'm not going to actually, because this is very different audience, let me first ask, does everyone know who Bayesian is? Yes, okay, excellent. I don't have to explain that. So of course, what I'm not going to talk about is whether, the Bayesian like eating fish or not, or whether, eating fish makes you clever or not. So that's not what I'm going to talk about. Instead, what I'm going to talk about is about, Bayesian methods and also artificial neural nets and their applications in fisheries management. So that's what I'm going to talk about. So this is a joint project with the Sujieto from CSIRO, Yedipila from School of Mathematics and Physics, and Yemin Lei from School of Mathematics and Physics as well. So Yemin is sitting here. He has been doing a lot of work, on this. Yeah, so I start with a quote from John Schaeffer. So he's an emeritus professor from the University of Washington. Yeah, so this is very nice quote about how difficult it is to manage fisheries. Basically, you don't observe where the fishes are. Yes, you can catch some fish, but you don't really know where they are exactly, and they're moving around. That makes things very difficult. And to answer the question of how we can manage fisheries well, we need to have some knowledge about fish abundance. And then based on the models that we estimated using fishery data, then we can come up with some
management reference point. So this is what our project is about. I'm going to explain that in more detail in the next slide. I'm going to give you an overview of here how things work when we talk about stock assessment. We start with the sun catch and effort data, so you know which boats goes to which place to catch how much fish and how much time they spend there, and whether this is in winter or in summer, you know, a lot of other information. And based on this, what people do is people will try to standardize the so-called catch rate. So the idea of catch rate is how much fish you can catch if you just spend 1 unit of effort. So, but the problem is, as you can see here, you may have different boats. Some boats, they are better at catching fishes. Some boats are not so good at doing that. And the weather condition may be different. So there are all kinds of differences here. If you simply divide the amount catch by the effort, that's not going to work. It's not going to tell you how much fish is out there. So that's not working very well. Instead, you need to standardize all these things. So given all this data, you can standardize to information that looks like this. So you want to say, for this particular kind of boat, if you go to this particular place, you know, under a particular, let's say in a particular season, how much fish we can catch. And that gives us a better idea of the relative abundance of the fish. Then after that, based on these numbers, then you can develop some models on the population growth. Then you can use it to calculate the absolute biomass. Okay. And what we did in this project, so this is a very difficult problem. People have been working on this for more than half a century. And in this project, what we are doing is we are developing first a kind of neural net or artificial neural net for standardizing the catch rate. And we also develop a Bayesian approach for this stock assessment. So I'm going to talk about these two methods in the next few slides. So I start with talking about the artificial neural nets for standardizing the catch per unit effort. I believe a lot of people have at least heard of artificial neural net in the last few years, because this is what behind the so-called deep learning technology. So it has become really quite popular. These models are inspired by how human brain works. Mathematically, they are really very simple. They're just interconnected simple computational units. So you can express them in terms of very simple mathematical computations on a very simple graph. That's it. Yeah. So I'm not going to give you a tutorial on this though. But the main take-home message is these networks are very powerful. They can represent a lot of complex relationships. So that's why we are particularly interested in solving the difficult problem of standardizing catch rate. And what people have done in the past is they do not take the dependencies between the variables into account. What they do is they simply fit all the variables available and use it to construct artificial neural nets for predicting the catch per unit of effort. Yeah, and in our case, what we do is we exploit the structure, the dependency structure between the variables, so that we are not going to introduce unnecessary dependencies between your target variable and the predictor variables. That's the key idea. And how does this work in the case of CPU standardization? We did some simulation study and also did some study on the northern prawn fishery. For the simulation study, we generated data that simulates the distribution of highly migratory species. So basically, the fish will move around to space and time. And the fishing sites are initially random. But we assume that the boats are equipped with better and better technology over time, so they become better at finding out where the fish are. And the catch is also affected by technology as well. So roughly, this is how we generate the data. We developed some classical statistical models, namely generalized linear models and generalized statistical models for predicting the catch. And we also look at the two artificial neural nets here, what people have tried and what we have developed in this project. And these are the results. Okay, this is a little bit off. So for the species distribution, this is the ground truth species distribution, and these are the distributions predicted by the 4 different models. The take-home message here is, if you look at artificial neural nets, they basically have similar trends as the true underlying distribution. So it actually captures the spatial-temporal distribution of the fish really very well. While for GLM and GAM, they didn't manage to capture the underlying distribution well. If you look at the difference between full and the spatial-temporal and the redeveloped, you'll notice that although they look similar high level, but actually this is more similar to the ground truth distribution. And what we are really interested in here is the standardized CPUE, or the relative abundance of the fish. So the black line is the ground truth, and the curve that's closest to the black line is given by the spatial-temporal artificial neural nets. If you look at the red curve here, the solid red curve, that's for the full artificial neural net that people have been using in the past. And it's not actually quite accurate. The reason that this is not quite accurate is actually it managed to overfit the data. Yeah. Okay. Almost done to this group. 5 minutes? Yeah. Okay, so that's good enough. And then we also did some severe standardization in the northern prawn fishery. So this is very important prawn fishery in Australia, but not much study has been done on this prawn fishery. We looked at the blue endeavor prawn, and we look at data from 1970 to 2050, so 2020. So that's 50 years of data. We have a lot of records there, and based on this data, we again tested the performance of the 4 different models that we use in the simulation data. Of course, the variables for this data set is different. They are different. That's why the formulas look quite different, but the ideas behind them are the same. So for the full artificial neural nets, basically you throw all the variables to the artificial neural nets, and then ask the neural nets to generate prediction of the catch. And in the case of spatial-temporal artificial neural nets, we want to incorporate some kind of structure in the network so that it's not going to overfit the data. And this is how the results look like. In this case, we don't have the true distribution of the fishes, but we can observe how much fish that we have caught according to the data that we have collected. And these are the distributions predicted by generalized linear models, and the 2 artificial neural nets. In this case, actually, they look quite similar, and we are still looking at these distributions more closely to see which one is making more sense. So some more validation is needed. They're high level, but all of these models are making some sensible predictions. And then how about the relative abundance for the standardized catch per unit of effort? If we compare all the models, overall the trend looks quite similar. This is actually what happens frequently in practice. All the models often seem to behave in similar way. But one thing that we noticed from by comparing the 2 different artificial neural nets is, if you don't take the structural dependencies into account, then the 4 artificial neural nets give you a result that seems to be highly unstable. Yeah. So again, this is preliminary result, and we are still looking at this, and then we need to do some further validation to see which one is the better one. This turns out to be a really difficult question to answer because we actually don't have a ground truth for us to evaluate the right answer. Yeah. Okay. So that's about computing the relative abundance. And I'm just going to quickly say a few words about estimating the biomass. So people have already used Bayesian methods for estimating the biomass. The general idea behind Bayesian estimation. I think a lot of you know of Bayes, so I think you have seen this equation many times. I don't have to explain this. But one problem with this general approach is you have to actually choose the prior in order to generate good performance, accurate results. In some cases, it can be very difficult to come up with the good prior. And if you have a poorly chosen prior, the performance can be pretty bad. We propose a new method for multi-pass Bayesian estimation. And the idea is you try to figure out how much emphasis you should put on the prior or how much emphasis you put on the data. So if the prior is a bad one, you are hoping that you can automatically figure that out and then put very low emphasis on the prior. And that's roughly the idea. How do we do that? We generate a sequence of probability distributions ranging from the prior to something that just depends on the data. And then you try to figure out which one is the best one in an automatic way. I'm going to skip the math here. I'm going to tell you about how the new method works on some simulation data and also the northern fishery data. This is how we generate the data. We use the so-called Schaefer model to model how the population biomass grows. And this is a standard equation relating to the catch and the effort. Basically, the catch is proportional to your effort and also to your biomass. So simple equations. And what we are interested in is to figure out unknown parameters related to the stock. In particular, we want to know the so-called carrying capacity, which is how much fish the environment can support at equilibrium. And R is the so-called intrinsic population growth rate that reflects how fast your fish grow, and also the catchability constants and also initial depletion, which is just the ratio of the initial biomass divided by carrying capacity. And the stock assessment model that we use is based on exactly the same equations in a slightly different formula. How does this work? We test our method MBE and the standardization method and also maximum likelihood estimation on the randomly generated data set using different priors. So by we specify a prior, that means your prior is concentrated on something that's very different from ground truth. And which prior is red? And red specified is something that's concentrated around your true model. So in all settings, MBE performs pretty well, but for Bayesian and MLE, they do not always perform very well. In particular, for Bayesian, if you start with the bad prior, the performance is quite bad. So these numbers are the relative or absolute relative errors over the parameters and the data set. Yeah. So this is how the method performs on the simulated data set. Overall, the MBE is much more robust. Even if you specify the prior incorrectly, you will still be able to get good results. If you manage to specify the prior correctly, that's good. It's going to figure that out and then try to make use of the prior. And so we also apply those methods to the northern prawn fishery data set, and these are the results that we obtained. So the key stock parameters are somewhat different here. Standardization gives a little bit more conservative estimate for the carrying capacity, but it provides a much higher estimate for the how fast the fish can grow. Yeah, so there are some differences here. Again, these are the things that we are currently investigating. We want to see which results makes more sense. And in terms of the biomass, these are the biomass curves predicted by the two methods. So again, MBE provides a somewhat more higher estimates for the biomass, and the Bayesian produces a lower estimate. Okay, so these are all the things that I want to talk about, and this is a summary of my mention. Yes, I talked about the two methods, Bayesian method and also method based on artificial neural nets for estimating the relative abundance and the biomass. And our current results suggest that these are quite promising. We are still trying to validate the results and the real data set. Okay, yeah, thanks for your attention. Any questions?
Questions?
Got a question for Emer in the chat. Novelty across space still needs to be detected by differences across time, right?
Oh, well, yeah, like sorry, I feel like I'm in the wrong question time, but yeah, the idea of looking at novelty across space does require one time step only, but then the potential for using that as like a baseline for monitoring then on top of that, if you're, looking after your one reef system or your one forest. If the hotspots for novelty are changing over time once you've done that spatial comparison, I think that's like one of the actual uses for this method once developed. I hope that was one of
I have a question about the neural nets. How easy are they to use, like other standardized tools that you can just plug your data into? Like GLMs are pretty easy to do in R, for example.
Yes.
I've never used neural nets.
Yeah. So yes, the question is about whether it's easy to implement the artificial neural net approach. Yes, compared to the standard GLM packages, I would say that it's not as convenient yet. You still have a few knobs that you need to tune. But now people have developed many powerful libraries for you to develop artificial neural nets. So they are not that difficult to use as well. Yeah, if you want to know more, I'm happy to provide more details about that and then provide some pointers to actually help people do that. Yeah, but overall nowadays, I would say that it's much easier as compared to at least 10 years ago. So 10 years ago, when you want to develop artificial neural nets, it was really a difficult thing. Now you can actually write probably in about less than 20 lines of code, you can actually train artificial neural nets. Yeah. Okay. Yes.
Is this the kind of like artificial application where you require that training and validation data set? And if so, how much of the data set did you have to set aside for the training purposes and that kind of thing?
Okay. So
it might not be that kind of structure at all, but
yeah. So I think it depends. The question is about the training set and validation set. How much data you should allocate to for training and validation. But I think this is really highly dependent on the specific application. People often use numbers like a 70-30 split, or maybe 80-20 split. But you can also see sometimes people do like 50-50. So there isn't a magic number that you can use. I would say that it depends a lot on the particular application.
What were you finding, for example, for your fisheries models was working well?
That's a really interesting question. I just actually let me go back to the simulation itself. Yes. So actually, this is really interesting question. If you do validation here, basically it doesn't work. The reason is because if you collect some data, let's talk about the real data set. If you collect some data, and let's say that you reserve 70% of the data for training and 30% of the data for testing. Actually, what we found out is, in general, this is not useful at all. The reason is because your validation data is likely too similar to your training data. And if you use the validation set performance to choose the best model, most of the time it's going to fail. The reason is because what we are trying to predict involves making predictions on unseen situations. Yeah. So by using a similar data set to do validation, it's not going to tell you how good your model is. We found out the problem in the simulation data set as well. So I think this is still a problem that people don't know how to answer very well yet. If you read the fisheries papers, yes, they report like R-square, or MSE or other like AIC, a lot of metrics there. But I think we should look at those metrics with a little bit, caveat. We shouldn't take those metrics as indicating whether your model is perfect or not. Yeah.
Just a
very broad question for both of you. So this is a engagement between UQ, subheading CBCS, but not just CBCS, obviously much more broad than that, and CSIRO. I'm just curious the degree to which you have been engaging with CSIRO partners and how you found that interaction for both of you.
Oh, sure. My CSIRO collaborator is Chris Doropoulos, and he's great with having a conservation and restoration approach to coral reef ecosystems, and that's not really something that I've got. I'm more ecological and now starting to be more quantitative ecological. So having him to talk about not only just applications for conservation and restoration, but also where to go when we go to Jigaroo, and what places are worth sampling and what places haven't been sampled. Yeah, he's a great collaborator for his expertise in
and application of the models that you're putting together for his purposes within CSIRO.
Yeah.
Obvious next steps for it. Do you expect that will happen?
Yeah, and just our data sharing as well. I went to a conference recently where other people had shown interest from their conservation restoration background. So yeah, so he's very much helpful in that sense. Yeah.
Great. Okay, and so in my case, we work with Shijie Zhou from CSIRO. So Shijie is senior principal fishery scientist, and he has a lot of experience in fisheries. And I don't have a lot of experience in fisheries because my research area is more on the theoretical or algorithm side for analyzing data. But I think that I can make this project like a nice combination of different expertise to solve a very difficult problem. And Shijie and Ye and I are actually supervising Yemin. So I think this is a very nice team. So I know a little bit more about the algorithms, but Shijie can always tell whether what we are doing makes sense. In terms of whether that generates sensible results for fisheries. Yeah, so I think it's working pretty well. Yeah. Thank you.
All right, one question for you.
Yeah.
So you in space, you're looking for that novel ecosystem, a novel system, and you were given the example of like Heron Reef and maybe going to Visit Island and a couple of others. Have you thought about the difference between something being locally novel and globally novel? So, you might have Heron Reef, you find one site and it looks really novel, but then you go to Lizard Island and that same assemblage is everywhere. I was just wondering how those ideas play out.
Yeah. That's something we'll be doing in that third aim that I was talking about. So not only looking at novelty within a reef system, but then across the three. And I am expecting that things would look very different if you're looking just within Heron versus using samples that are separated by such large distances between three different regions. And so I think that something I've done in the past a bit is look at coral communities not via taxonomics, but looking at their traits or morphological traits. And so I think that is something that may transcend the species differences that we'll see in those obviously very separated regions, and show us something a little bit more interesting as to whether a novel assemblage across all of those three has ecological meaning outside the bounds of these are just very different latitudes that we're seeing coral communities at. Yeah, so we'll get there.
Great. So if there's no other questions, I'd like to say big thank you to those two presenters, Emer and